This video will introduce an algorithm to calculate the value of B1 from a known reflection pattern using negative simplification method. The need to use negative simplification method comes out because positive simplification method has a weakness, which occurs when S mod t has low value, which makes simplified pattern almost the same as original pattern. Thus more simplification process is needed to reach simplified pattern with t equals 1. In positive simplification method, if a simplification step is inefficient, the next steps will be inefficient too, as shown in this example. A simplification step is said to be inefficient if t prime is larger than half t. In the first step above, t prime equals 9, which is very close to t equals 10. This inefficiency is continued to the next steps. Negative simplification process can be used to get out of this sticky situation. It relies on the fact that if t is larger than half s, the reflection pattern has a negative incoming angle. Previously, it's been shown that a reflection pattern t over s has identical shape but opposite direction with pattern s minus t over s. Consequently, it can be shown that a reflection pattern t over s has identical shape and direction with pattern t minus s over s. Hence, reflection pattern 9 over 10 can be written as minus 1 over 10. The number of steps can then be greatly reduced. In the diagram below, dotted right arrows show operation t prime equals t minus s mod t, subtracted by s prime. Since s prime equals t, then t prime equals minus s mod t. The other parameters and operations are identical to positive simplification process. Here's an illustration of positive versus negative reflection pattern. The left picture shows reflection pattern of 9 over 10, while right picture shows reflection pattern of negative 1 over 10. The numbers inside the circles are number of reflection for each reflection point. In the 9 over 10 pattern, at first reflection, the light is thought to have circled around the center for 9/10 cycle. At second reflection, the light has gone 18/10 cycle, which is already more than one cycle. In the negative 1 over 10 pattern, at first reflection, the light is thought to have circled around the center for negative 1/10 cycle. At second reflection, the light has gone negative 2/10 cycle, which means it hasn't reached a full cycle yet. In the 9 over 10 pattern, to reach first position, the light takes 9 segments, which is counted as 9 times 9 divided by 10 cycles, or 8.1. Hence C1 equals 8. In the negative 1 over 10 pattern, to reach first position, the light also takes 9 segments, which is counted as 9 times negative 1 divided by 10 cycles, or negative 0.9. Hence C1 equals 0. In the left, the numbers inside the circle are sorted according to the direction of light propagation. In the right, the numbers inside the circle are sorted in opposite direction of light propagation and get negative sign. At 10th reflection, the light front comes back to incoming point. Generally, adding s times reflections doesn't change the position of light front. Hence, B1 with negative value can be converted to positive value by adding it with s. Let's compare the results between positive and negative simplification methods. The goal of both methods is to calculate the value of B1 of a reflection pattern characterized by t over s. In this example, it's 10 over 21. Positive method produces value of B1 equals 19, while negative method produces value of B1 equals negative 2. Those values are equivalent, as 19 equals 21 subtracted by 2. Negative simplification process has some advantages compared to positive method. First, it uses simpler formula to calculate t prime. Second, negative method can quickly escape from a series of inefficient process such as in positive method. In the example above, first step produces absolute value of t prime equals 10, which is inefficient since it's pretty close to 11. But this inefficiency is not continued to the next step, since it already produces absolute value of t prime equals 1, hence the value of C1 can be immediately determined, i.e., 0. Negative simplification process also has some disadvantages. It involves negative numbers, which increases the risk of errors when it's calculated manually. In modulo operations involving negative numbers, following rules apply. If A mod B equals C, then A mod negative B equals C, negative A mod B equals negative C, negative A mod negative B equals negative C. Which mean that the sign of the result only depends on the sign of left operand, regardless the sign of right operand. Negative method uses equation t prime equals negative s mod t, hence t prime has inverted sign of s, like this example. The original pattern with t over s is 34 over 89 has positive s, hence t prime is negative. First simplified pattern with t over s equals negative 21 over 34 has positive s, hence t prime is negative. Second simplified pattern with t over s is negative 13 over negative 21 has negative s, hence t prime is positive. If a reflection pattern cannot be simplified efficiently using positive method, then negative method will calculate it efficiently. But negative method is not always more efficient than positive method, like this example. Negative method simplifies pattern of 34 over 89 in 7 steps, while positive method can do it in only 4 steps. Although generally, negative method has better efficiency than positive method because it can quickly get out of inefficient simplification series, unlike the positive method. In worst-case scenario, negative method needs twice as many steps as positive method. Minimum efficiency of positive method occurs when s mod t equals 1. In this case the process requires as many as t simplification steps.